my pen not working? There it is. Your region tells you your x's go from 0 to 2, and your y's go from 0 to 2 minus x. So that's your entire region. Yeah. And then it asks you to find the probability that 2x plus y is greater than or equal to 1. If I solve for y, I would have 1 minus 2x, right? So got a y-intercept of 1. You've got a slope of negative 2, so it's going to end up hitting here at 1/2, right? And you're asked for the probability associated with that region. I would probably do the complement, personally, because I think it's easier to set it up with that part. So I'd find the probability in that area and then do 1 minus that. So I would do integral from 0 to 1/2 and integral from 0 to 1 minus 2x of whatever the PDF was that you were given. The x squared plus 2y over 4, and then do 1 minus that. That'd be how I would approach it. Because otherwise, you're going to need to use two integrals either way, right? Because either I've got different bounding bottom curves, or I've got different bounding left curves. So if I do it the other way, I'm going to do two integrals no matter what. Yeah. Other questions? Yeah, Trace. Yep, got a test next Thursday. Oh, no, sorry, next Tuesday. I lied. Next Tuesday, yeah. What's that? Well, maybe Thursday we're gonna have more stuff on it because we got a little bit more to do on Thursday. I was trying to space it out with the linear exam. That was why. And then
they end up just right next to each other every time.
I was trying to space it out a little bit so we weren't having to do it back to back. I know. It's not the best semester for taking tests. Yeah, one more to go, and then the final. All right. Other questions at all? All right. So let's continue on with what we were talking about last time, and we'll get into some other stuff today. So last time we were looking at, random samples or independent distributions, and looking at calculating different expected values for finding PDFs or calculating probabilities based on the fact that we had independent distributions. So again, this one actually tells us we have independent. But if you see random sample, that also means independent. Okay? All right, so let's look at this one. It says that we've got independent exponential distributions that give you different means, though, for these particular ones. So we're not doing a random sample from the same distribution, but we're going to handle it in a similar way. This one asks us to calculate the probability that the maximum of them is greater than 3, right? Well, what if the maximum is going to be, well, let's start with a different idea. So the idea, start with a different thought. We want the probability that the maximum, and let's just call it x1, x2, and x3 for the different random variables, is greater than or equal to 3. Now, based on what you know about exponential distributions, would you like to calculate it in this fashion, or would you rather do the complement? I'd probably rather do the complement, right? Because in particular, if I do the complement, then I have it, it's not quite a CDF. It's the same one we were working on last time. It's not necessarily right as a CDF to start with, it says maximum. However, we know that we can set it up in an exponential distribution as a CDF. We have a nice formula for that, don't we? Okay. So I think it's a little bit easier to talk in this case to do the complement. And it actually will help in terms of the problem. So let's set up the complement. I guess it does say exceeds 3. They probably shouldn't have the equals on that part. Doesn't matter. It's continuous, but just to be accurate. Let's approach it from the complement standpoint here. Let's do 1 minus the probability the maximum is less than 3. So I want the maximum of the 3 different observations that we make. All of the maximum to be less than 3. So what does that say about each of the observations relative to 3? If the maximum is less than 3, what has to be true? They're all less than 3, right? If the maximum is going to be less than 3, then all of them have to be less than 3. So this is probably that x1 is less than or equal to 3, and x2 is less than or equal to 3, and x3 is less than or equal to 3, right? The important word here is the and, right? What are we assuming about the 3 different distributions? They're independent, right? So how can we break up that probability? Multiply, right? So that's the probability that x1 is less than or equal to 3 times that x2 is less than or equal to 3 times that x3 is less than or equal to 3. Each one of our random variables here is an exponential distribution, right? And we've got them all set up now as a CDF question, don't we? So what can I say about if I use 1, 2, and 3 in that order for what we have for the means? How would we write the probability that x is less than or equal to 3 using our CDF? What would you have for the exponential? Do we remember what the CDF is for an exponential? So the PDF is 1 over theta. That's an ugly looking theta. E to the minus x over theta, right? What's your CDF? Yeah. It's 1 minus e to the negative x over theta, right? So the first one here will be 1 minus e to the negative 3 if the theta is 1. The second one will be 1 minus e to the negative 3 over 1.5. And the last one will be 1 minus e to the negative 3 over 2.4. You could simplify it, but that looks good enough to me. That one okay? All right. So the reason why I did this example is because one of the things that you might be interested in when you're talking about random samples is what's the biggest in your sample? What's the smallest in your sample? What's the middle value of your sample, median? Right? There's different values that you might be interested in. If you've done any statistics at all, I know I've mentioned this several times this semester, but some of the statistics that you're interested in with samples is what's the low value, what's the high value, what's the median, what's the lower quartile, 25th percentile, what's the upper quartile, the 75th percentile. Those are different things you might be interested in. And what you might want to be interested in is what the distribution of those variables might be. Okay? So we refer to those things as order statistics, and you can come up with nice formulas for the PDFs for any, if you have a random sample of size n, what the PDF is for any of those things that are put in order? Okay. What we're going to be interested for our cases is, what does the PDF look like for the maximum of a random sample, and what does the PDF look like for the minimum of a random sample? Okay, and we're going to use exactly this idea that we did here, where we're going to have the max is less than or equal to a number. That means all of them have to be less than or equal to a number, so we end up with a product. Okay, so just to develop that, let's suppose that x1, x2 out to xn is a random sample from a distribution with PDF, I'll use little f of x, and CDF, capital F of x. Not specifying what the distribution is, but I do want to be able to refer to the PDF and the CDF of that distribution. Okay. So again, remember when I say that we have a random sample, I'm treating each of the x sub i's as its own random variable. They're all independent, but they all have exactly the same distribution. Okay? Yeah, you can do it. Okay? They're all independent, but they all have the same distribution. So they all have the same PDF, they all have the same CDF. Okay. So we're going to let a new random variable be a function of these things. So let's let y be the maximum of the x1 out to xn. Our goal here is to figure out the PDF for y. That's our goal. Okay. Using the same type of techniques we've talked about before, let's start with the CDF and take a derivative. So again, by definition, the CDF is the probability that the random variable is less than or equal to some number. We'll call it little y. And y is defined as the maximum of all the x's. This looks exactly like the setup we just had in the example problem, doesn't it? Okay. All right. So again, and notice why this is in this part of the chapter. We've talked about y being a function of x, so y is some sort of a transformation of x, right? Now, before today, we were talking about y was a function of a single x, and then we found the inverse function, right? Now y is a function of several x's, so that technique's not going to work, so we have to be a little bit different in our attack on this. But the attack is just what we did in the previous example. In order for the maximum of all of them to be less than or equal to a number, what has to be true about every single random variable? Yeah, it has to be less than or equal to y. Exactly. All of them do, right? So this is the probability that all of the x sub i's are less than or equal to y. Right? Agree? But now, this means this is a product, isn't it? That was what we did. They're all independent. So this says that x1 has to be less than or equal to y, and x2 has to be less than or equal to y, and x3, and, right? They're all the same. Or they all have to, they're all to, sorry, try that again. It's a long and statement, and we handle ands as products when we have independence, right? So this will be x1 is less than or equal to y times the probability that x2 is less than or equal to y times, all the way up to xn is less than or equal to y. But look at each individual one. What can I say about each of these? How are they set up? It's a CDF question, isn't it? So that first one's going to be what? Just using the notation, what's it going to be? Yeah, capital F of y. And notice they all have the same distribution, right? So it would be, if they had different distributions, it would be F sub 1 of y, right? But they're all the same distribution. So that would be capital F of y. What will the next one be? Another capital F of y all the way out to capital F of y. What's a better way to write that product? Good. F of y to the nth power. Yeah, exactly. Now I have a formula for the CDF. How do I get to the PDF? Derivative, yeah. So little g of y will be capital G prime of y. Now we get to use a chain rule. What will be the derivative of this piece here that's underlined? Well, there will be a little f of y out on the outside. Yeah. Good. Yeah. I got to use a chain rule, don't I? I got to bring the n down in front, decrease the power by 1, and then a little f of y. Okay. So if I know the CDF for the underlying distribution, and I know the P, well, if I know either of them, I can find the other. But if I know the CDF and PDF, I've got a nice formula here for the PDF for the maximum. Okay. Well, not only can we do this for the maximum, we can also do it for the minimum. Okay. We just have to do one little thing first before we do for the minimum. So let me call it, I'll call it W this time, just to give it a different letter. And I'll use an H this time rather than a G just because I'm using a different variable. There's nothing special about using the letter H except that I didn't want to use G again. Okay. Okay. So notice I started this the exact same way, right? I started talking about the CDF for W. W is defined as the minimum of all of them, right? Now, in the previous part, we said that if I have the maximum is less than or equal to a number, then all of them have to be less than or equal to that number, right? Can I say the same thing for the minimum? Just because the minimum is less than or equal to a number, does that mean that all of them are less than or equal to that number? No, right? Right? If the minimum is less than or equal to the number, that just means that the lowest one's less than that. The rest of them could be above it, right? Can you rewrite this, though, into a statement where you know that the minimum does have a certain relationship to W? Yeah, I can do a complement. Good. That's exactly right. Let's do 1 minus this. So if I do the minimum that the minimum is greater than W, that would be the complement, right? Now can I make a similar statement? If I know that the minimum is greater than a number, do all of them have to be greater than that number? Yeah, I can make a similar statement, right? So this is now 1 minus the probability that all of the x sub i's are greater than W. And now I have an and statement again, don't we? Yep. So this is 1 minus x1 being greater than W times x2 being greater than W times xn greater than W. The way those individual factors are written currently, are those CDF questions? No. Can you convert them to CDF questions? Yes. It's a complement again, isn't it? Right? Each of these will be 1 minus the CDF, won't they? So this will end up being 1 minus the CDF of F or the CDF, the f of the, try that again, the CDF of the underlying distribution. So it's f of w raised to the nth power, right? This will be 1 minus the CDF. This will be 1 minus the CDF all the way out. There's n of them, right? Now do the same thing. If I want the PDF, I'll take the derivative of the CDF. Derivative of the 1 out in front will be 0. You'll bring the n down in front, make it an n minus 1. What's the derivative of the inside going to be in this case? When I take the derivative of just this piece. Good. It's negative little f, right? But there's a negative out in front, so they'll cancel. So we'll end up with little n, 1 minus capital F of w to the n minus 1 times a little f of w. Nice symmetry to it, isn't it? The maximum is just the CDF. The minimum is the complement of the CDF, but it's just about the same formula. If you want a PDF for a statistic that's in the middle, you'll end up, you'll get something that looks kind of like this, except that you're going to get a combinatorial coefficient thing, a binomial coefficient thing on the inside, or on the outside. It's not that hard to develop. It's just not one that I'm going to be interested in for our purposes. Yes? Okay, so let's say I have those 4 numbers. I want the maximum to be less than 18. Does that guarantee that everything is less than 18? If the maximum is less than 18? Okay. Say I want the minimum less than 3. Does that guarantee that the minimum is less than 3? What's the minimum of this? 1. But does it mean every single number had to be less than 1? No, just the smallest had to be less than 1, right? That's why I had to flip it. Okay. But if I say that the minimum is definitely bigger than 3, well, then that one doesn't work anymore. But if I said the minimum is definitely greater than 0, then they all had to be bigger than 0. That's why I had to flip it. All right. So let's see if we can put these formulas to use to answer a couple of questions. That's the whole reason why I did it, right? Ah, there's one. Look at that. Yeah. Not the previous one, because the previous one wasn't the same distribution for all 3 variables. Right? The distributions had different means. So I couldn't use that formula for that. They have to be identically distributed. That's why you need a random sample. Okay. All right. So let's look at this one. Random sample from a particular type of distribution, right? Uniform on the interval from 0 to 1. And we want the minimum of x1 and x2. Okay. What we just came up with is that the PDF for that then should be 2 times 1 minus the CDF times the PDF, right? And I'm just putting a sub x in there so that we know that I'm talking about the CDF and the PDF of x, right? Our n is 2 in this case, isn't it? It says the minimum of x1 and x2. So the formula we just had in the previous one, I'm just putting in n equals 2. So I have a 2 out in front and a 1 is my exponent. So what I need to know is what the CDF is for x and what the PDF is for x, the x1 or the x2. What type of distribution do we have? Uniform. On the interval from 0 to 1, right? So what is f of x going to be? 1. And then what's the CDF going to be? If you needed to go back and do it, it would be the integral from 0 to x of 1 dx, isn't it? What's that answer going to be? It should be dt, I guess, technically. It should be just an x, right? Yeah, so it's just x. Antiderivative, right? Just got to make sure you have your endpoints lined up right. Okay, so what are we going to get for the CDF for y then? And 2 times 1 minus, technically it's a y, right? Since I use a y. Yep. Plugging in the y for the x. Do you see that? I actually put the answers here for you. So do you see that one? It's that one here, right? I just put the y in for the x into the CDF here, right? That's where the y is coming from. Why do I know that the y values have to go between 0 and 1? Well, what are your possible values for the x's? 0 to 1, right? So my y's also go from 0 to 1. The smallest possible value you can get out of y is 0. The biggest possible value you can get is 1. Pretty unlikely that you'd get 1, but they both have to be 1, right? But you can get it. Yes. Remember, your definition of CDF is what? It's that, isn't it? Okay, my interval, my lowest x value is a 0. It says go up to x. I mean, I'm using our definition for our CDF. That one okay? Let's do the next one here. This one's actually asking us for the probability of the minimum. But let's see if we can figure out. Let's ignore what the problem's asking for. We'll do it at the end here. But let's see if we can figure out the PDF for the minimum. All right, so if I have y is the minimum of x1, x2, and x3, regardless of the distribution, what's your PDF going to look like? Yeah, the n, so the n in this case is 3, and then times 1 minus the distribution to the second, and then times little f sub x of y, right? That's the PDF. But notice this problem's this problem's actually asking us for an honest to goodness probability, right? If I'm able to write the CDF, I can usually get these probabilities a little bit easier. Yeah? Notice in the derivation of our PDF, we also came up with the CDF for y, didn't we? What was the CDF? Well, this was the derivative, right? It was the derivative of what? Yeah, it was just the 1 minus to the third power, right? We agree? That's just in general, isn't it? That is the CDF for y. This is referring to the CDF for x. So in this particular problem, we're using an exponential distribution, right? What is the CDF for your exponential distribution? Yeah, 1 minus e to the negative x. Good. Notice that your 1 minuses will cancel. I just have an e to the negative x to the third power. All I get is e to the negative 3x when I'm done. Or 3, that should be a y, since I have a y in there. I just end up with an e to the negative 3y when I'm done. That is the CDF. That's a nice formula, right? So let's go back over here. This problem's asking for the probability that this is my y now, isn't it? Y is greater than 1. How do I convert that to a problem, question about the CDF? 1 minus. So I have 1 minus the probability that y is less than or equal to 1. This is my CDF for y. So we end up with 1 minus e to the negative 3. Just plugging in the y for 1. The 1 for y, I mean. I said that backward. Mm-hmm. That's what the problem's asking me. I let y be the minimum. Right? The problem's asking us for y is greater than 1. It's written flip-flop, but that's what it's asking me. So just using the formula we came up with to get this answer. That one okay? The next one has to do with a maximum. If I remember right. Oh, look at that. They give you a PDF for claim amounts. Doesn't matter what the context of the problem is. You just have a PDF here. We want the expected value of the maximum. That's what it's asking for, right? Expected value of the largest. So we want the expected value of the maximum of a random sample of size 3, right? This is 3 such claims. How do we compute expected value again? What do you have to do? Yeah, you do, right. So if I want the expected value of y, I would need y times the PDF for y over the entire interval, right? In this case, my interval is going to go from 1 to infinity, since my x's go from 1 to infinity. That's what we need to compute, isn't it? Doesn't matter what the distribution is or what the PDF is, that's what we need to compute, right? So in particular, I've got to figure out what my PDF is for y so that I can actually do this integral. How are we going to define our y in this case? It'll be the maximum of the 3, right? This is the largest of the 3 claims, so I need the maximum. Using the formula we came up with before, not worrying about what the distribution, the specific distribution is for x. What was our formula for the PDF of the maximum? Okay. Good. Yeah, it's n times CDF to the n minus 1 times PDF, right? That was our formula. We have the PDF. How do we get the CDF? What do we need to do? Integrate, right? Our lower limit is 1. Our upper limit will be the x, because I got to go from 1 up to an x. And then integrate your PDF. Antiderivative for 3 over t to the 4th, or a 3t to the negative 4. Good, that's exactly right. Negative 1 over t cubed, right? When you're done, then you'll get a 1 minus 1 over x cubed. That'll be our CDF. So going back over here again, I've got 3 times 1 minus x cubed squared, because that's the CDF, right? Times 3, y, sorry. Forgot to change my variable. And then times a 3 over y to the 4th. So again, n times CDF to the n minus 1, that's what we have here, and then times PDF. That okay? All right, so then if we want expected value, we know what the formula is for expected value. Oops, forgot my y. Y times the PDF. I'm going to need to multiply all that out before we can do an antiderivative, right? Given 9 over y cubed. If I take my this times that piece, right? If I take that here times that whole thing here, I'll get a 9 over y cubed. We square out the other part. We should get a 1 minus 2 over y cubed plus a 1 over y to the 6th. And then distribute. So distribute that 9 over y cubed over everything. Now we need to anti-differentiate each piece. That sounds like fun. It's not too bad. They're just powers, right? The first one will be a 1/2 y to the negative 2. The next one will be a 1/5 y to the negative 5. And the last one will be a 1/8 y to the negative 8. And what happens when you plug infinity in for y? It goes to 0. Good. So we just then, and notice that we'll subtract those off, right? So we'll have a positive 9/2, a minus 18/5, and a positive 9/8, and I'm not going to bother adding the fractions together. I'm not as worried about, in this particular instance, I'm not as worried about the calculus as I am the process. Do you understand how we got all the pieces? What questions do you have? All right. Well, that's doing the independence and the maxes and mins. We're going to play a little bit more with independence. So let's look at this question. We've got, don't worry about the context, just worry about what the problem's asking you. You've got a random variable z defined in terms of x and y. You're told that x and y are independent. And it asks you what the variance of z is given the variances of x and y. So first question, before you do anything else, what does that minus 5 do to the variance? Nothing, right? It does absolutely nothing, correct? Remember, constant shifts do nothing to the variance. It's just a shift, right? Variance is a measure of spread. Minus 5 is a shift. Shifting doesn't spread out anything more, right? Okay, so the 5 is not doing anything. So all we really need to worry about is what's going on here. Remember again that we have that nice formula for variance of ax plus by in general. What's that formula? In general, not worrying about independence of x and y or not. In general, what's this formula? Yep. Good. Yep, it's 2AB covariance, right? Cool. Good, good, good. You did remember. All right. Problem says they're independent. Right? So what happens to the last term? 0. Good. This goes away to 0 since they're independent, right? All right. So going back over to our problem then, What's the A value? And the B value is -1. Good. So the variance of variance of Z will be what? Good. 9 times the variance of X plus the variance of Y. Remember again, you're squaring that coefficient, right? One of the errors that I see students make is subtracting a variance off at that point. Okay, so be careful with that. Make sure you square the negative. Okay. What do we end up with there? 11? We're done. There. Cool. Let's look at the next one. Actually, I'm going to skip the next one. The next one's still the same theme. You just have to be a little bit careful because instead of having 2 random variables, you have 3. So you'll have to play a little bit around with the covariance piece. Not too bad. You just have to play around with it a little bit. You'll be adding some more things on at the end. Okay. So not worried about that one. Well, the reason why, because remember how you have to do, just if you want to go through and practice, remember again your variance of this thing is expected value of the square, right? And then minus the square of the expected value. Right? Notice that when you multiply this stuff out, you're going to get an x1 times an x2. You'll get an x1 times an x3. You'll also get an x2 times an x1, and an x2 times an x3, an x3 times an x1, and x3 times an x2. So you're going to get covariances twice for all the combinations of the variables. That's why I said you have to be a little bit careful with what you're adding, but it's the same concept we did when we came up with the other formula. All right. Anyway, I'll let you practice that one. It's not bad, I promise. Okay. Let's do something that leads us into the next section instead, which is this idea of moment generating function of a sum. All right, so they give you that x and y are independent, and they give you they give you the moment generating function for x, and they give you the moment generating function for y, and then they ask you to compute the moment generating function for the sum of the two things. Okay? All right, so remember how the definition of moment generating function? So if I have a random variable z, let me use w. We typically use z for standard normal, right? So let me use a different letter. If z is a random variable, doesn't matter what it is. How do we define moment generating function again? Good. E to the t times the variable, right? Okay. So in this case, if our w is x plus 2y, let's look at what our moment generating function will be. That's the definition, right? Our definition of moment generating function is expected value of e to the t times random variable. What do you think we should do first? Good. Plug in for the w. Good. Yeah. So far, so good. Okay. What do you think we should do next? Yeah, distributing sounds like a good idea. So we distributed the t through. What do you think we should do next? Ooh, split the exponent. I like that. When you have a sum in the exponent, you split it up as a product. Good. I'm going to write this. I'm going to flip my t and my 2 around and regroup a little bit. So now I have a product. I've got e to the 2x times e to the 2t times a y. Now, at this point, without knowing something more about x and y, I'd have to stop, okay? Because I don't really have any way. And remember, expected value does not behave nicely necessarily with respect to products unless what's true? They're independent, right? Since x and y are independent, I can do the next step. What do we want to do next? Split the expected value. Now remember, that's because they are independent. You cannot do that in general. Okay? So from here to here is, I'll write it in red just to emphasize. That's where we're using independence. Okay? That you cannot do that in general. Okay? Okay. Now, remember the problem asks us to find the moment generating function for this random variable that we defined, the x plus 2y. We were given the moment generating function for x, and we were given the moment generating function for y, so we probably want to use those. Looking at the first term, what is that exactly the definition of? That is the moment generating function for x, so we have e to the t squared plus 2t times. Then the next one's not quite the moment generating function for x. This should be a what instead? A t, and now it's a 2t. So what have we done? We've taken out a t and put in a 2t. So how do you think we should write down that second one? What do you think we need to do? Yeah, we're going to the moment generating function for y and replace the t with a 2t. Yeah? And now if I simplify this a little bit, we'll get e to the, I'm going to rewrite it. I'm going to write it as 4t plus, what is that, 13t squared? Now, the reason why I rewrote it, let's look at the three different moment generating functions we have now. This is literally the reason why I'm doing this problem is to lead to the next section. Okay. Let's look at the three different moment generating functions. They all have exactly the same form, don't they? As a matter of fact, what type of random variable that you know has this form for its moment generating function? And there's a reason why I flip-flopped my exponent for that answer to help you recognize it. What is it? It's normal, yeah. Okay, this is a normal distribution. Notice they all are normal, right? So in particular, when I do the sum of these two normal distributions, I get another normal distribution. Okay. Sum of normal is normal. What happened with the means here? Did I add that wrong? Oh no, it's okay. I thought I added it wrong. What happened with the means? The mean for x would be what? What do you look at for the mean for the x? The coefficient on the t, which is a 2, right? Mean for the y is 1. What would be the, without doing any of this other work, what should the mean of this thing been? 4, right? Because it would have been the mean for that plus 2 times the mean for that, right? Should have been 4. Notice that's what we get here, isn't it? The 4? Okay. How about the variance? What's the variance for x? Be a little bit careful. The coefficient on the t squared is what for the normal? It's not just the variance, it's variance over 2, right? So remember the coefficient on the t squared is half the variance, right? So in this case, the variance for x would have been 2, and the variance for y would have been 6. Yeah. Okay. The variance for this one should have been 26. All right. I feel like I made an error somewhere along the way here. In any event, we should have added the variances. Why am I getting something that's Squared. 13 plus 6 plus 6 is what I'm getting another one. Now, anyway. Yeah. How did I get this? What happens when you add these exponents? Right? Why am I getting? I should be getting something. My variances should have matched. I'm not sure why my variances aren't matching. Well, in any event, I'll come figure out where the error is later. In any event, the idea here was that A, how we got the moment generating function, and B, the fact that when I added normals, I got a normal. Okay, that was the big thing.
Isn't 13 right? It's half the variance. The t squared. Variance is 26.
Oh, yeah, I was squaring my variance. Yep. The 13's right. Sorry. I was thinking 6 squared. That was my problem. Yeah, I should be adding 2 plus 4 times 6. So it should be 26. Yep, thank you. That was my problem. I was squaring the 6. I'm like, why is it too big? No, you're right. Thanks, Trace. I was going to drive me crazy later. Yeah. So the variance of my x is 2. My variance of my y is 6. And remember here we would have the variance would be the variance of x plus 4 times the variance for y. So you'd have 2 plus 24 is 26. For some reason my brain was squaring the 6. All right. The last one, I forgot to put what the question was. This is just another practice with the covariance part. I'll leave it for practice. This one's asking you for the variance of m plus n. That's what the problem's supposed to ask you. I'll leave it for practice. It's literally just using the same formula we've been doing. Okay. I cut it off when I copied it. All right. So let's do some more problems here with moment generating functions, and in particular, using the moment generating functions to help us what the distributions are for when we add random variables. So that really is the whole point of section 4, is to recognize what sums of different random variables are if we know what the underlying distributions are, all right? Or the distributions are for each piece. So let's look at this first one. It starts with 2 independent binomial distributions, and then asks us what the moment generating function is for the sum. Okay? So the first thing we need to remember is that if x is binomial with parameters n and p, then the moment generating function for x is what? Good. That's our moment generating function for a binomial in general. Okay. So this one's asking us for the moment generating function for the sum. For what we just did in the previous problem, if we had the moment generating function for the sum, what did you do to the moment generating functions? When we did the moment generating function for a sum, what do you end up doing to the moment generating function of each piece? Multiplying, right? So the moment generating function for y, should be the moment generating function for x1 times the moment generating function for x2. Again, what's the important piece of what allows us to multiply here? Independent, right? That's the important part. The reason why we need independence to do that, I'm just trying to remind for review purposes. Moment generating functions are defined as expected value, right? When you do a sum in the exponent, that changes to a product. So I need the expected value of a product, and I need to be able to distribute the expected value. That's why they have to be independent. Okay? So now, according to this, I know what a binomial distribution's moment generating function looks like in general. So I would do 1 minus p plus pe to the t to the n1 times 1 minus p plus pe to the t to the n2. The only thing that's different about x1 and x2 are the n's, right? Now that I have the same base, what can I do with the exponents? Add them. And now what is that the moment generating function for? What kind of distribution has that as its moment generating function? It's a binomial, right? What's the n value? n1 plus n2, and the p is the same p, right? So what's the point of this? Must have some sort of a point. If you have independent binomials with the same probability of success, sum of independent binomial is binomial still. And all you do is just add the trials. Okay. Why is that important? Well, it's going to be important later on when we talk about the central limit theorem. That's what we're going to talk about, and actually last day of class, the central limit theorem. But what's important is that, remember that we had Bernoulli random variables? Remember Bernoulli was a single trial, right? Okay. So if your x is Bernoulli, then if I draw all of my x's that are independent from a Bernoulli, so if I have x1 plus x2 plus xn, so I have a sum of independent Bernoullis. Well, Bernoulli can be thought of as a binomial where your n is 1. This is going to be binomial of np. So a sum of Bernoullis is a binomial. The reason why is because, remember, your moment generating function for a Bernoulli was just this, right? It was that to the first power. When I multiplied a bunch together, I just multiply it by itself n times. So sum of independent Bernoullis is binomial. That's important. Okay. The reason why it's important is because I can think of a binomial distribution as a sum of a bunch of other distributions. And that's going to help us out with the central limit theorem. Okay. That's why we care. I promise we care. Well, at least I care. You may not still care. People care. Okay. All right. Let's look at the next one. Before we do anything, let's remind ourselves of what geometric distributions count. What did a geometric distribution count? Yeah, number of trials until first success, right? Was there another distribution that counted number of trials relative to successes? Negative binomials. It was number of trials until the rth success, right? Okay, let's see if that relates here. We've got a random sample taken from a geometric distribution with p equal to 1/3. The first problem asks for the moment generating function, right? I'm going to write this out longhand, but the idea here is to recognize what's going on with the moment generating function in terms of the sum. So your moment generating function for a y would be, again, that's the expected value of e to the ty I don't expect you to write this out every time. I'm just re-emphasizing what's going on. Okay? Replace the y with the sum. That's what we have, right? Do the exact same thing we did in that first example problem dealing with moment generating functions. Distribute the t and break up the product, break up the sum as a product, right? We would have expected value of e to the tx1 times e to the tx2 times same thing for x3 times same thing for x4 times same thing for x5, right? And again, that's nothing to do with independent. That's just the fact that our random variable was defined as a sum, right? The independence piece is what we need for the next part. Why do I know it's independent? What's telling us that it's independent in this case? Random sample. Good. The random sample is telling us that we have independence, right? So since we can have independence, we can break this up. This is why I'm telling you don't have to write this out every time. And now each of those is now a moment generating function, right? That's a T. That's ugly. Let's write that a little bit neater. Okay. Now, notice I didn't take into account anything except for the x's were independent, right? But now what else do we know besides independence? They also all have the exact same distribution, right? So this is just going to be the moment generating function raised to the fifth power, isn't it? Okay. So again, when we do the sum of independent random variables, the moment generating function will be the product of the moment generating functions. Okay. What is the moment generating function for a geometric? P e to the t. And in this case, I told you the p was a third. Yep. 1 minus p will be 2/3. And then say that again. Oh, the 1 minus. Good. It's 2/3 e to the t. That way. Okay. Sorry about that. And that'd be raised to the fifth. So we did our geometric moment generating function raised to the fifth power. What does that look like? Is that the moment generating function for a negative binomial? Yeah. With our p equal to 1/3 and r equal to 5. Again, important part here. Sum of geometrics gives you negative binomial. Okay? That's the whole point of this section, by the way, is to recognize these things. Or vice versa. I can think of a negative binomial as a sum of geometrics, no matter what negative binomial I have. Questions on that one? Yeah, Trace. Yeah, just add the r. As long as they have the same p's. Yeah, you would just add the r's. Yep. Yeah, you have to have the same p's to get the same base. Yeah. Okay, cool. We've already talked a little bit about this before. Now we have independent Poissons with different means, but it asks us to find the moment generating function for the sum. Well, again, Moment generating function for a sum is product of moment generating functions, right? Okay. What is the moment generating function for a Poisson? Yeah, good. Right? So if I want the moment generating function for y, in this case, what would we multiply together? It's just the 2, yeah. And then e to the t minus 1, right? And then e to the 4 times e to the t minus 1. What's going to happen in your exponents? What are you going to end up with? Good. Good. And what do you recognize that as the moment generating function for? What kind of random variable has that as its moment generating function? Poisson with lambda equal to 7, which is just the sum of the lambdas, right? That makes sense? The last part, Poisson is a discrete distribution, so you'd have to add it up from 3 to 9, right? Do a sum of those things, or use your calculator. Use the calculator's Poisson CDF function on it. So this, if you wanted to write out part C, we'd have the sum from 3 to 9. Remember, your Poisson PDF is lambda to the x e to the minus lambda over x factorial, but I'm using a y in this case since they told me the random variable was y. So that would be how you'd have to do it since it's discrete. I figure it's good to write it down as a review, right? Questions on that one? Again, important part of this, sum of Poissons is Poisson. Independent Poissons is Poisson. No, no. So if sum of independent Poissons is Poisson. And in particular, all we did was just add the lambdas, right? Okay. So this one is the same kind of idea, except it's doing it more generally. And it has a constant in front, or that A is a constant. Let's say the A weren't there to start with. And we'll play with what the A does here in a second. What if your W was just the sum of the X sub i's? What would your moment generating for W look like? Good. And then times that e to the t minus 1. Good, exactly right. So if I didn't have the a's, I would just add the lambdas, right? Oops, I forgot my equal sign. Okay. Because again, you would just multiply them all together. When you multiply them all together, each of them has an e to the t minus 1 that you can factor out and then just add the lambdas, right? What does the A do? Well, let's go back and look at, this goes back to that first example that we did when we had the 2 out in front of the Y, right? If I just had W was A times X, just a W with just a single A, just a single X, okay? If I did expected value of e to the t times W, And there was a reason why I did it this way in that first example. I replaced my W with A times X, and then I just rearranged things. What does this look like now? Good. AT gets plugged in for T into the moment generating function for X, right? Okay. That's all that happens. If I have a constant times a random variable, I just take that same constant and stick it where the T is. Okay? Right? So remember, your definition for your moment generating function is e to the tx, right? So I've replaced my t with at. Okay? So when I have an a in all of these, all that's going to happen is that my a is going to get stuck with the lambda sub i's here. So you're going to end up with b. So the a is going to be in there where all the t. I'm sorry, I lied. The a goes in where the t is. Sorry, it's not out in front here. Where does the a go? It goes here, doesn't it? So it has to be this one. By the way, it can't be these other ones. What do these look like? A and C. What does that look like the moment generating function for? Or have a t and a t squared up in the exponent. That looks like a normal, right? Sum of Poissons isn't going to be normal. Okay. Sum of Poissons is Poisson. And again, when you have a constant that's times your expo or times your random variable, you're going to take out the t and put in a t. Well, the t is on the e to the t here, right? So I would have e to the a t rather than just e to the t. Oh, that's out of time. All right. We'll do a few more of these on Tuesday. And again, what we're going to emphasize on Thursday, whatever day it is, next time. That's why I usually say next time, because I never remember what day it is. Thursday. We'll do more of these. And again, what I'm emphasizing in this particular section is what the sum of independent random variables becomes, what the distribution is. So after we talk on Thursday, as well as having a review for the exam, I'm going to post a little Google quiz. It's not for a grade, but there's a little Google quiz in there that just quizzes you on what types of sums of distributions or other types of distributions. Okay? This is a practice thing. It's not a quiz. It's just a practice quiz. Does that make sense? This is another thing for review to try to remind you of those things. Anyway, we'll do more of this next time. Have a good one. See you on